Good morning, everybody. The allergies that I had last week developed into a sinus infection over the weekend. So I sound terrible. I will probably sound like I'm hacking up a lung up here. But my doctor assures me that I am allowed to go out in society. How do we say this anymore, right? Doctor gave me a clean bill of health, blah, blah, blah. So we'll see if my voice lasts. Today is not brought to you by Dayquil, the makers of NyQuil. Today is brought to you by prednisone and doxycycline. There you go. Only one person emailed me yesterday reminding me that I had forgotten to post the exam topics. Have you guys just given up? Like it doesn't matter anymore? Be sure, when I forget stuff like this, be sure to bother me about it, right? Chances, I have these topics all set and ready to go in a document and I just simply failed to post them to Canvas, right? So if you feel like something's up, be sure to let me know. I went one step further here, okay, and gave you the topics, right, by chapter, right? So there can be a little bit more organization. Maybe that'll help you a little bit on the exam as you open the exam, right? The exam questions are in a random order. You can go through and say, oh, okay, Doppler effect. Well, I know Doppler effect is going to be from chapter 60, right? Just to kind of organize your cheat sheet, organize your thoughts, whatever it is you do, right? Let me know if giving you the chapter numbers helps. I actually had to pull the book out and look at the chapter numbers to make sure I got this right, because you guys know me in numbers, right? It's just they don't stick in my brain at all. So pretty sure I got all of those topics and things correct. So 7 topics, right? 7 questions. I even, like I usually do, highlighted the conceptual questionnaire. SHM, simple harmonic motion. I just got too lazy to cut and paste apparently. Any questions about these topics, things that you're not sure, when I throw the topic up there, what that means?
So the exam gonna have each of these topics on a separate?
Always, yeah. But it's 2 questions per page, and then there's usually the 7th question all by itself. That's just because I print 2 questions per page. So yeah, you guarantee that the one multiple choice question on the exam is going to be about simple harmonic motion, right? There's going to be a Doppler effect question on the, right? So when you get to that, oh, okay, it's Doppler effect.
After the 6 now, how many are there?
So we have one more exam after this, right? This is the 4th exam. We take 5 exams. And just looking forward a little bit, your final exam in this course is the last exam in this course. In other words, the final is not intentionally comprehensive. What do I mean by that? Physics is comprehensive, right? Everything we're doing now, we need to understand energy and all that kind of stuff, right? But I'm on the last exam, which is the 5th unit's exam. I'm not going to go out of my way to get a question from unit 1, right? But well, maybe you won't need to know yet. It's thermodynamics, so it's stupid. Yeah, so it's just the last unit's exam. We take that in here on the Thursday before finals week. Okay, so what's the final, right? What are we doing during finals week? What always happens after an exam? An autopsy, right? So our scheduled final exam time during finals week is your last exam autopsy. So that's just how I roll, right? Other questions, either about the topics, homework in general, life choices, what?
For traveling waves, is it something about transverse and longitudinal?
Yes, so specifically when it comes to, I use that term traveling waves to distinguish it from standing waves, okay? So like, knowing like how to read like that function right there. We did a couple of examples in class. I think I gave you some homework about like, if you're given a function, right, how do you find the wavelength of this thing? Right? If you can read the amplitude, you can read the wave number, you can read omega, and then you can find out pretty much which direction is this wave going? It's moving to the right. How do you know? It's got a negative sign inside there, right? So I think your homework reversed the order of omega t and kx. It doesn't matter. As long as there's a difference between them, it's moving right. If there's a positive sign, it's moving left. So like, that's what I mean by traveling waves. Any other clarifications on these topics? Yeah.
Can you go over number 3 and read chapter 16?
Chapter 16? Yeah, let's do that. But let me real quick just make sure, like, how do you identify a simple harmonic motion problem?
The acceleration is constantly changing.
It is, but that's true for waves too. Like, what are some of the giveaways for a simple, like, different from a wave? What's sort of like unique about simple harmonic motion? What's like the picture? What objects? What's involved when you've got a simple harmonic oscillator? Spring, right? So like, simple harmonic motion, that could be what's the maximum acceleration? How fast is it going at a certain position? It could be like conservation of energy that involves a spring, right? It could be, it's kind of a big thing, but at least you know that you're dealing with that toolbox if you've got an object that's either attached to a spring, being launched by a spring, like kind of, or even just has spring-like behavior. A trampoline could be a spring, a bungee cord can be a spring, a mattress can be a spring. And often the problem, if they don't say there's a spring, an actual spring there, we'll say treat this thing like a spring. If you see, if it springs, that's simple harmonic motion. Dead giveaway, right? Simple harmonic conceptual, you're just going to be at like know where an object undergoing simple harmonic motion has its maximum speed, its maximum kinetic energy, its its accelerate. Where's the acceleration zero? Where like the ideas surrounding what's going, like where is the object in its motion, and what can we know about that spot? Traveling waves we talked about. So traveling wave, right, will be a transverse or longitudinal wave going places, right? The wave will have speed, that kind of stuff. Sound intensity, like what's kind of the giveaway for sound intensity, especially the unit? It's decibels, right? Sound intensity is going to involve like that decibel scale, right? Doppler effect. All Doppler effect problems have two players in them, right? Two actors. The person observing the sound and then the thing making the sound. So there's going to be objects like passing each other or moving, right? But somebody's going to be listening to a sound. Somebody's going to be making a sound. And you're being asked to solve for like what the observer hears or what's the observer's velocity or something like that, right? And then standing waves, like what's the dead giveaway with standing waves? They're standing there. But what's the picture? The football, right? The antinodes and the nodes. And then there's details, right, between standing waves and a pipe versus standing waves on a string. Like with strings, we count antinodes. And in pipes, we count nodes to figure out which harmonic we're on. There's special rules when it comes to pipes closed at one end. But you always know that you are dealing with a standing wave problem because they're talking about fundamentals and harmonics and, right? There's specific language surrounding all that. So these are the contextual clues, the clues that are being given in the writing of the problem that will orient you to the topic at hand, right? And if your cheat sheet's kind of organized by topic, or literally your cheat sheet just has 7 sections on it, right? that correspond to these 7 things, excuse me, then you'll at least have a better chance of orienting yourself during the exam. Okay, let's see. So you said chapter 16. I remember that part. 3 and 8. Oh, I remember numbers. So again, my apologies for only posting that this morning. I should have done that last week. Oh yeah. This is a beautiful problem that all of you hate. If you like numbers, and this problem defies numbers. All right. So, what do we know? We know that the tension is the same. So like if we have 2 wires, and I'm gonna call this wire number 1, I'm gonna call this wire number 2. Okay? Then we know that the mass of each of these 2 things are the same, right? We know that the tension in these wires, this right symbol, Mr. Bailey, is the same. And so mathematically, right, we would use symbols to indicate relationships between these things. And they want to know the speed of number 1, don't they? I mean, the speed of the wave on the longer wire, that would be V1. That's what I'm looking for, okay? They gave me V2, 229 meters per second, so I better write that down, okay? And it doesn't seem like much else, right? It seems like there's kind of a lack of information and a way to get traction into this problem. So we go and we start looking at, well, I'm being asked for a speed. I've been given a tension and a mass, and oh, I do know something about lengths, don't I? Yeah. What's L1? Close. L1 is the longer one, so it's twice the length of number 2, isn't it? Right? They tell me twice as far apart. So again, I don't know what those numbers are, but I do know the relationship between those numbers. I would point out now that you could make up numbers at this point. When things are the same, it usually means it doesn't matter what they are. Okay? In physics and engineering, right? When you have equalities between things, chances are it's going to cancel out and deal with itself. So if you wanted to feel comfortable and put numbers in here, you could just make up lengths, you could make up masses, you could make up tensions, okay? But let me show you why it doesn't matter. Let's go back to problem solving mode. We need a connection between these things. Lengths, masses, tensions, and speeds. Is there anything in the chapter on traveling waves that connects these ideas together? Yeah, what is it? It's that equation that tells me the speed of a wave depends on the material that it's traveling in. And in the case of a string, that's going to be the material properties of the string, the tension and the mass per unit length. Tomorrow in lab, you're going to investigate tension, mass per unit length, how those changes affect standing waves by manipulating this equation. Okay, so there's my relationship, and I think your book writes it as the force divided by the mass divided by the length. It's the same stuff. I know it looks completely different to you, but the force is the tension and mu is the symbol that's usually used for mass divided by length. Okay, So we know we want to find V1. That's like, I want this, and so that's going to be the square root of T1 over M1 divided by L1, isn't it? Okay. And now I'm going to start I'm going to substitute. So like the T's are the same, aren't they? So I can just write that as T. I can just write this as M. I don't have to keep writing subscripts anymore because they're going to be the same tensions. So I'm just going to write T over M. And then is there a substitution we can make for L1, something we know about the length of 1 compared to the length of 2?
2L.
Yeah, it's 2L2, isn't it? So if I come in here and L1 is equal to twice the length of 2, right? So, all right, so now I got to figure out what happens there. When something's in a denominator like that, the denominator of a denominator, what's the rule? What do you do to it? Yeah, you like flip it up to the numerator, don't you? So this is the square root of 2L2 times, you know what, I'm only going to bring the 2 up. I'm going to cheat a little bit because I know where I'm going. M over L2, okay. What is V2 equal to? Like, I know it's a number, but like in terms of the ideas here, the relationships, what's T2? It's T over M over L2, isn't it? Where the tension and the mass are all the same, right? What is T over M over L2 with a square root? It's V2, isn't it? So I can substitute, right? There's lots of different ways to think about this. Are you guys comfortable with the idea that the square root of x times y is the same as the square root of x times the square root of y? Yes, no? A lot of you are looking at me with blank faces. That's a math rule. Let's pretend like we've forgotten that. So if I solve over here for V2, or T over M over L, I could square both sides. Okay, so there we go. T over M over L2 is equal to V squared. So that's going to be the square root of 2 times V2 squared. This is what V1 is now, okay? And now, on the right-hand side here, I have a number, don't I? It's 2 times a number I already know, 229, square rooted. And I've got the answer, okay? And I did it without having to know what the mass and the tension, right, and the actual lengths were. Again, I know this kind of drives you up the wall. One of the reasons I signed it, right, is to just open your mind and expose you to different ways of going about thinking about solving problems, getting you out of that, well, I'm just going to turn the crank on math and see what happens, right? But trying to think your way through it. Will something like this be on the exam? Probably not. Like, this is kind of a hard problem, isn't it? It requires putting together a lot of different pieces. You should know by now that I would consider this a harder problem for this chapter, and I'm going for more of a medium level difficulty, right? Okay. Hard because you've got a lot of pieces to put together, and it's a thought process that you're not real familiar with. Yeah.
I know you just showed us how to do it, but how come it wouldn't be, or how come we can't just do like V2 or V2 times 2 since it's twice as long on V1?
I mean, that's, now that we know that, we could do that, right? But this is a way of showing, part of science is not just getting an answer, right? It's showing how you got there so that we have deeper understanding as to the relationships between things. So yeah, that's kind of a probably not very satisfactory answer to your question, but So the message I'm trying to give you right here is, oh my gosh, I didn't understand a word Mr. Balogh just said. I got lucky on this problem because the Discord or my friend or somebody said, just take the answer, multiply by square root of 2. I don't understand what's going on. Focus more on the concrete aspects of traveling waves, right? I've told you that this is from chapter 16, right? Which involves traveling waves. Know how to read a wave function, all that kind of stuff. Let's see, so did I answer your question there suitably? Okay, and then number 8. I should take prednisone more often, I can remember numbers. Oh, okay. What kind of problem is this? This is Doppler effect. How do you know it's Doppler effect? Something's moving, something's making a sound, there's a frequency involved, right? And so immediately my brain can focus on my Doppler effect toolbox, right? And so let's see, Doppler effect toolbox, what does that look like? That looks like the frequency that an observer hears is equal to the frequency of a source, V plus V observer all over V minus V source. Okay, so that's like my equation. And then the Mr. Balogh method is towards and away. You would assign directions, right? There would be vector sign, positive and negative signs on the observer and source velocities. But as the homework loves to do, it's throwing curveballs at you. Because, okay, so 1440, what is that? That's the thing making sound, right? It's producing 1440. So I know the frequency of my source is 1440 hertz. Okay. Speed of sound, they gave me 343, that's good, okay. Ooh, okay. 131. If you want to do this problem incorrectly, then you might assume that that's the frequency that the observer hears. But that's not the case here, right? We got to read a little bit more carefully. 131 is a change. What's the symbol we use in physics for changing something? It's a delta, isn't it? The change in frequency is 131 hertz. We know that number, but it's the difference between two observed frequencies. The frequency that the observer hears as they're moving toward the object, and the frequency as they move away from the object. Again, visualizing here, right? We got this car, and it's giving off sound, okay? And you in another car, not pictured, right? You're coming towards it, and then you pass it, right? And what we know is the difference, right? If you hear 1,131 coming towards it, okay, then we know that this one's going to be 1,000 because the difference between them is 131. I'm just making up numbers there. But again, I'm trying to like conceptualize, get a picture in my brain of what's going on. They've given me the difference, the delta between those two frequencies. Okay, so that's what's going on. And this delta equation is basically where I start, because the frequency the observer here is moving towards will be shifted up, and the frequency that the observer here is moving away will be shifted down. And that means I've got two of these that I need to apply. The frequency as we move towards the siren, and then the frequency that we have as we move away from the siren. So turns out my change in frequency is going to be frequency of source V plus over V minus, okay. And the source is not moving, right? So what's the speed of the source? 0, so I can just put 0 down there. So toward, if the observer is moving toward the source, positive or negative sign? positive, so we would put positive V observer. Okay, minus frequency of source, V plus, V minus, and then 0 on the bottom, and then as an observer moves away, minus VO, there we go. Okay. Excuse me. What do we know in this huge, horrible equation I've got here? I mean, it looks overwhelming, doesn't it? It's just got a lot of stuff in it. But can we substitute some stuff in here? What are we after? Like, what's the goal? V observer, isn't it? I see it in 2 places in this thing, which is already causing me to kind of quake in fear. This is a number, right? This was given to me. These both are the same number, not 2s, so I'm just trying to underline them. Okay. Those are the same number. What are all these V's? The same number, right? They're all numbers. I'll solve it your way, I guess. Here, hold on a second. So delta F, which was in my problem was 131. So 131 equals frequency of source 1440 over 343 plus V observer all over 343 minus 1440 343 minus V observer all over 343. I'm pretty sure, yeah, I got all my signs right from that equation. I just substituted in the numbers. So I'm gonna be real uncomfortable and you guys are gonna be cheering, right? I don't like numbers, you guys like numbers. So we need these. We need those 2 things right there. We need them all by themselves on one side of this equal sign, right? So that means we gotta move them to one side and all the numbers to the other. Okay, so now we just need math tricks. We just need the ability to work through this. What happens if I divide all sides by 1440? If I do it to the left side, I have to do it to the right side, right? And I've got to do it to every term in my equation, right? So what happens to the 1440s on the right hand side? They go away. Okay? What happens if I multiply by 343? Then on the right side, those would cancel out, right? I'm looking again for ways to get the numbers away from these V observed. So what am I left with? I'm left with the number 343 times 131 over 1440. I don't like calculators, so I'm just going to leave them like that. What am I left with? 343 plus VO minus 343 minus the observer. What do I do with that minus sign that's sitting outside my parentheses? Distribute it through, right? So 343 plus V observer minus 343 minus a minus makes me a plus. Oh, what's 343 minus 343? Mm-hmm. And what if you have one apple and I have one apple, we put our apples together, how many apples do we have? 2 apples. 2, right, equals 131, 343 over 1440. And there you go, right? Everything's a number now. Take whatever number that is on the left-hand side, divide by 2. And you've got your... Again, giving you this problem, what I would consider a difficult Doppler effect problem, under the assumption that if you can do this problem, you should be able to do a problem where you're standing still and an ambulance drives by, right? And I'm only asking for like, what's the frequency that you hear as the ambulance approaches you? That's what I would put on an exam, right? Or maybe as it goes away from you, right? So, you know, I give you problems that are harder in the hopes that they make the easier ones easier, but if I know anything about students and my own predilections as a student, I always tried to make things as absolutely hard as I possibly could on every exam that I took, even though it wasn't that hard. So. You probably prefer that I give you a problem exactly like this one, right? But then I can't find out what you know. So Rahi, did I answer your question? Other questions? Yes.
Chapter 17, number 6.
Number 6 on chapter 17. You said number 6?
Yeah.
Okay. We know the length of our wire. Okay, so since it's well, we know it's chapter 17, so we know it's going to be standing waves, right? But I can tell this is a standing wave problem because it's asking me about fundamental frequencies. It's telling me that the string is stretched between two fixed ends, like the fixed supports, right? So what's on the either end where it's fixed? What do we call that? Call that a node, right? Okay. All right. So I'm thinking, looking at my cheat sheet, I'm looking at standing waves. I know it's a standing wave on a string or a pipe. String, because the string's involved in the problem. So what do I know about that? I know that the nth harmonic is going to be n times the fundamental, which is V over 2L. So that's one thing. Let's see, is this going to help me? You're giving me lengths and masses and tensions. Does that have anything to do with a wave? Hint, we just did it earlier. The speed, this was part of the toolbox I gave you for standing waves on strings. The speed is equal to the tension divided by the mass per unit length. They've given me a length, they've given me a mass, and they've given me a tension. Can I find out what the speed of this wave is? Sure can. For clarification, the speed of a standing wave, since the standing wave just stands there and really has like a speed of 0, we're talking about the speed of the wave on the string as it goes down and then bounces back and comes back, right? Because a standing wave is made up of traveling waves that are perfectly tuned with each other to form those harmonic patterns. So it's the speed of the individual waves on the string. They travel back and forth. Okay, so if I can find that speed, then I should be able to find the fundamental frequency, which is V over 2L. I know the L, so this is a matter of finding V. I can go ahead and just substitute that in right now, I guess. This would be 1 over 2L times the square root of T over mu, if I just kind of wanted the whole package together. But now I see a trap. Units are always a trap. So I've been given newtons for the tension, that's good. But what do I have to do to that length? Got to put it into meters, right? 40 centimeters is 0.4 meters. Because there's 100 centimeters in a meter. Alright, so that's 2 over 0.4 meters. Square root of my tension, 170. All over, okay, so for mu, right, that's my mass divided by my length. Well, I converted my length into meters. What do I have to convert grams into? Kilograms. 0.0067 kilograms, because there's 1,000 grams in a kilogram. Divided by 1,000. So that's gonna be the mass, 0.0067, all divided by my length, 0.4. Toss it into my calculator, see what happens. Apparently it should be 126. Because I failed as a teacher to turn the student view on for the homework that's already due. I have no idea if this one randomizes the numbers or not, so. That's okay. Natalie, did I answer your question? Do you mind me asking where you were stuck?
I forgot to convert them to.
Okay, so it was a unit issue, yeah. I can't remember how long it took me to remember to fix units. I was like well into my senior year in college, where I was really kind of, when I got to the point where it was habit, right? You always put the units in the unit system of the problem. Thing with physics though, as you get further into it, we start using kind of some weird, we use weird units that oddly make the problems easier. Quantum mechanics is strange. Anyway, we invent unit systems where everything has units of 1, so we can safely ignore the units. Physicists are weird. And then there was that class I had to take on condensed matter where all the unit systems were inverted. So it wasn't an x, y, or z axis, it was a negative x, negative y, negative z axis. It was bizarre. It was just, I held on for the ride in that class because now you're asking a dyslexic person to work in inverted unit system. I did not become a condensed matter physicist, that was not gonna happen. Sorry, trip down memory lane. See what units do to a person? All kinds of PTSD and stuff, crazy. Other questions? Yeah.
I just have a question about chapter 10, number 7. It was the screen pull, and we had to decide if it was like a negative and a positive.
I'm gonna have to look at, oh, I'm sorry. I don't remember it offhand, it was too long ago. You said number 7?
Yeah.
Block is moved, okay, yeah, using the data, determine the total work done by the restoring force, right, okay. And then they had like negative, okay, yeah, so they're asking you
Yeah, I just wanna know how you determine if it's like,
positive or negative.
yeah.
So it's the work done by the restoring force. In other words, the work of the spring. So if we, in part A, if we stretch, like, remember work is equal to force times distance. But what happens if the force and the distance you're going are opposite each other? Yeah, you get a negative work, right? So the distance S in this case, or X, is to the right. But which way would the spring be pushing or pulling on that block? It would be to the left, right? Because the string is being stretched out, so the spring goes backwards. And so I've got a force to the left, I've got a displacement to the right. That's gonna be a negative work.
So, I understand.
Get it? Okay. One of the ways I try to, unless I'm specifically targeting, does a student understand like positive, negative work, which I would have done in conservation of energy anyway. One of the ways I get around this, like when I'm writing your exams, is I'll often ask for the magnitude of something. Like what's the magnitude of work, right? That way you can answer positive or negative and I'll just ignore your sign. I just want the number, right? But again, if I wanted to know the direction, I would ask for it. I know it doesn't feel like it, but I am on your side. Cheering for you. trying desperately to be biased in good ways towards you as I grade your exams. I have to close my eyes a lot. Close my eyes, find the next paper, turn it over, start grading, so I don't know whose is whose. Other questions? Yeah.
Can you go over to number 4 on chapter 17?
17? One of these days, I'm gonna start just putting polls up in class, that way you guys before class can vote on which ones you wanna see, and that way I can organize them by chapter. Not have to go back and forth. Or maybe Wiley Plus will let it so I can just open up all the chapters simultaneously. What would that be like? I'm sorry, it was number what? Okay, what's going on? Okay, so I know fixed supports and the word harmonic is coming up in this problem. Standing waves, right? What kind of standing wave? Strings or pipes? Looks like a string or wire. So it's not an air. Okay, same for find this individual waves travel on each wire. Okay, so what do I know? I know they tell me, okay, they've given me a frequency, but it's like two different situations, right? The frequency 653 hertz on wire A is the second harmonic. On wire B, the 653 is the third harmonic. So using that word harmonic correctly, what do I know N is for my wire A, my red wire? The N here is 2. And what's the N gonna be for the blue wire? It's gonna be 3. The harmonic number and N are the same. All right, they want us to find speed. The fundamental frequency is V over 2L. The nth harmonic is N times that thing. So I should be good to go. Because 653 is going to be equal to F2, which is 2 times V over 2L. And I know the length, 1.9 meters. Okay. And then 653 is for the blue wire is going to be equal to N, which in this case is 3 times V over 2L. To this physicist, that problem looks done. I mean, I didn't get an answer yet, but everything I need is on the page. And away I can go. Did I answer your question?
Yeah.
Where were you getting stuck?
Just kind of up in the middle.
Yeah, so you kind of get the setup and get the thing in mind. Yeah. The reason I should be asking that every time somebody asks a question is I want you to see that people are getting stuck in the same place as you are. You are not the only person stuck, right? You're all in the boat together of seeing these things for the first time, and so it can be, I don't know, maybe a little bit comforting to know that other people are suffering with you.
Yeah.
Other questions? Yeah.
Chapter 10, numbers 8 and 9.
Good questions today. Doing really well. 8 and 9. Okay, so there's that problem, and then, okay, so these are the same, same concept and idea here. okay? We know it's from chapter 10, which we know is the simple harmonic oscillator chapter, simple harmonic motion chapter. But again, dead giveaway, the word spring is in this problem, okay? So I know I'm gonna be thinking in terms of that big scary toolbox, right? So we've got sort of some setup here. Looks like I've gotta zoom out just a bit. Okay, so I can get the whole thing to fit. We know the mass of the pellet. I could start making a list if I wanted to, but I'm more concerned with figuring out what part of simple harmonic motion. Oh, okay. Okay. It goes to a maximum height, okay? And they want us to find the spring constant. So when I'm not sure of like an approach, this doesn't seem like a simple harmonic oscillator, like something that's bouncing back and forth, right? This pellet just gets launched, okay? So, specifically in chapter 10, but in general, when I'm not sure if this needs to be Newton's laws or kinematics or energy or momentum or whatever, I always default to energy. Like I just try that first, because it's usually the thing that can be set up the fastest, right? So if it's gonna turn out to not work, I'd rather know that was something that I can set up quickly versus say Newton's laws, which takes a lot of setup and free body diagram and a lot of mental capacity and all that kind of stuff. I'll do the hard stuff if I'm forced to do it, but let's try the energy stuff first. Aside from that, there's examples in the textbook, and I did an example in class where we had a similar situation. We used energy to find out. So again, those are the kinds of things that you hopefully are picking up on as I do stuff. Okay, so how would I do this with energy? Remember setting up energy. The setup is that we have final and initial and where zeros are. That's part of our visualization for energy. Okay, so there's two different zeros that we need to worry about, and they can be at different places. They don't have to be at the same place. Zero for gravity, gravitational potential energy, which I always put at the lowest point in the problem. They're measuring from here, I might as well reference from here. And then there is a zero for the spring. But you are not allowed to pick where that zero is located. That zero is picked for you so that spring potential energy makes sense. So where are we going to pick zero for or where are we going to assign zero for the spring? At equilibrium, at the place where the spring is not stretched or compressed, it's the resting length of the spring. So this will be zero for my spring. This will be zero for my gravity. And again, it's okay that those two zeros are not in the same place. All right. For my initial position, it'll be loaded down here, and for my final position, it will be at maximum height. This drawing's a little bit confusing because it's kind of like a before and an after sort of thing, right? It's not like it's kind of going up and doing that at all, right? The ball's really just going up is what it's doing. Okay, so with final, initial, and my zeros picked, I can go ahead and start writing out my conservation of energy equation. Since there's no air resistance and there's no other friction in this problem, my work done conservative is going to be what? I realized I reverted. This is how we did it for you guys? No? I can't remember how I wrote down conservation of energy for you guys. No, I know, but was it work non-conservative plus energy initial equals energy? It wasn't that way. I did it right the first time? It was that? Okay. I learned it one way. Different books over the years have done other things. I'm on prednisone. things happen. Okay, so there's no work non-conservative, okay? Let me make some more room here, 0 equals, all right. Final energy, I'm looking only at my final point right here. What are the questions that I ask myself to figure out energy? What's one question? Is there potential? Like, and now there's 2 forms of potential, right? There's gravitational potential, so is there mgh? And then the other one is there spring potential, 1/2 kx squared? Is this ball at 0 for gravity at the final point? No, so there is going to be mgh. When the ball is up there at the final point, are there any springs that are compressed or stretched? No, so there's no spring potential energy. Is it moving when it gets to maximum height? Nope. This is all I've got. Is it moving? Is it at 0 for gravity? Are there any springs up there? Right? Those are the questions you're asking. Okay, so we did that for the final point. Now we do the initial, right? Subtract all the initial. Add up all the initial energies. Is it moving down there at the launch? Like the instant you pull the trigger, is it moving? It's gonna move, but it starts with 0 velocity, doesn't it? It starts at rest. So no kinetic energy. Is it at 0 for gravity down there? Yes. Are there any springs that are compressed or stretched at that point? Yes. 1/2 kx squared. That's a k. All right. That's what I know. What have I been given? I'm given the mass. We know the compression x. They even gave it to me in kilograms a meter, so they're not trying to fool me with units. And they give me the height that this thing rises, 6.95. 1/2 kx squared equals mgh. Multiply by 2. Divide by x squared, so 2mgh over x squared. And I know all those numbers, so away we go. Where did you kind of get stuck?
It was just a setup.
It was set up. Okay, it's always set up, right? And getting those energies right. See, everybody gets stuck in the setup. Then you said number 10? 9, 8 and 9. Okay, so I make that a little bit bigger so people can see it. Okay. Okay, so say this is very similar to the last problem we just did. Similar in the sense that this is energy. So like the picture in my head is that there's some spring resting on a table, and then something is like being dropped onto that spring, right? We know the spring constant, we know the box's mass, and we know that the box makes contact. Oh, wait a second, do I even need energy here? It's undergoing simple harmonic motion as soon as the spring starts getting compressed. And yeah, I'll use energy. It's more fun. Okay, so this is 0 for the spring, 0 for gravity when it gets down there and compresses. I'm going to make this my initial point, and I'm going to make this my final point. And then I'm going to just start asking a whole bunch of questions. Whoops. Work non-conservative is equal to energy final minus energy initial. Again, they're not telling me anything about friction or anything else in this problem, so I'm just going to assume that's 0. When this thing gets compressed fully, is it moving? hold on a second, I'm worried about something. Magnitude of the spring's displacement at an instant when the acceleration of the box is 0. This isn't gonna help. I'm solving part B, is what I'm doing. We'll get back to part A later. Magnitude of the spring's displacement, yeah, okay, this will be good. So it's not moving down there, it's got no gravitational potential energy down there, but when it gets to the bottom, is the spring compressed? Yeah. 1/2 kx squared. And then initially, no spring, it did have some gravitational potential energy because it's not at 0 for gravity there, and it is moving. Okay, the amount of height that this spring compresses and the amount of compression that the spring experiences are the same. Wherever that box is at start to when it gets stopped by the spring, that's the compression of the spring and the vertical height that it went through. So this x and this h are the same, and that means that this is going to be nasty. Because this is a kx squared minus an mgx minus a 1/2 mv squared. That is quadratic in x. I gotta solve that for x. And so it's x squared, x, and then a constant. So quadratic equation, I'm not gonna do that right now. We'll get you the answer for B, okay? Part A, they're being somewhat sneaky. They should have dropped a hint on this one, but for the acceleration of the box to be 0, like right before it hits the spring, what's the acceleration of this object? It's been falling, right? So the acceleration is 9.8 meters per second. As soon as it comes in contact with this, so gravity's pulling it down, right? As soon as it comes in contact with the spring is gonna start pushing it up, okay? But the spring's force will not be equal to gravitation's force right away, right? The force on a spring increases the more we compress it. So really, what they're asking us to figure out is when does the force of gravity acting downwards on the box, is it equal to the force of the spring pushing up? That's what they're asking. The acceleration is 0 when the forces on the object are balanced. And for balancing, I would need the gravity mg to be equal to the spring force kx. And you might be saying, well, Mr. Bate, what about the minus sign on kx, right? Isn't it F equals negative kx? Remember what the negative sign in Hooke's law reminds us of. It's not meant to be an absolute direction, it's meant to be a reminder that springs always act opposite their compressions. In terms of magnitude of force though, I mean, another way to write this is that mg minus kx equals 0, right? We need them to add up to 0. So one of them has to be negative. You make mg negative and kx positive, I don't care, it doesn't matter. You end up with the same thing. So, determine the magnitude of the spring's displacement when the acceleration of the box is 0. Well, x is going to be equal to the weight divided by the spring constant. And I wouldn't put a problem like this on the exam. This is kind of simple harmonic motion, but is more like bringing in Newton's laws and stuff. Problem.
Would number 8 be like a good example of what the test, the one that we just did? Would it be that?
I could put something like, I could see me putting something like that for simple harmonic motion, either energy or something from like the toolbox, find omega, unlock something, now give me the period, give me the frequency, that kind of stuff. I mean, technically anything I put on the homework is fair game, but like, like I've told you, I'm trying to over prepare you, like this problem is reminding you of forces and reinforcing things like Newton's laws and acceleration and kind of keeping your brain up to speed on things. There's other reasons for me giving you homework, certain kinds of homework problems. By now, hopefully you realize that I'm not interested in you being able to regurgitate something you've already seen, right? I want you to show me that you understand the relationships between things. Other questions? I like these questions, good questions. Yeah.
Is there, will there be any problem from like a lab that was previously done on Big
We haven't had a lab on this unit, right? Tomorrow's lab is on standing waves, so yeah, I mean, you got 2 questions about standing waves. Tomorrow we're doing standing waves on strings. So again, it's gonna be practice with how do you know which harmonic you're on, and what happens when you change the tension in the string. So in as much as that lab is reinforcing your ability to problem solve and figure stuff out. I think last unit specifically, I said, wasn't it center of mass? Center of mass was on the exam, and we did center of mass only in lab. I didn't lecture on center of mass and then do a center of mass lab. I did the lecture and the lab together on the same day. That was me saving time. Do you guys want a lab final? Yeah. I learned 2 or 3 years into my career that lab finals in physics are dumb. Chemistry, I can see it. Microbiology, I could see it. Anatomy and physiology, I could see it, I wouldn't want to do it. Regular biology, I wouldn't do a lab final on regular biology, there's too many things going on. Other questions? Comments, concerns, opinions? Complaints? I'm open to your complaint. If you don't have anything for me, I don't have anything for you. I'm gonna rest my voice just a little bit. Please feel free to come on up and ask me any additional questions you may have. But I will see you tomorrow in lab.